webinar. My name is Tibor Fejes, and I'm the head of the training department here at Lightware Visual Engineering, and I will be the host for this event. And I will be staying in the background, monitoring the event and watching out for your questions. Our presenter today is going to be Gábor Kocsis, our technical trainer, and he has been teaching about IP in the past 20 years, so he has a lot of experience, and he's probably the best person to talk about the IP fundamentals in Lightware. So this webinar is called IP Fundamentals for Pro AV Professionals. So we didn't want to make an IP training or an IT training. We are not training IT people. We would like to give you some information about the IP things that you are going to meet or encounter during your Pro AV work. So I don't expect this training to be very in-depth. The well-known IT brands like Cisco, Netgear, Huawei, they have tons of very good training. So if you want to dig deeper into IT and IP standards, then they offer pretty good training materials. And this is the first part of 5. So we divided the material into 5 one-hour sessions. The first 3 are going to be about the fundamentals or the concepts that you can probably encounter. And the 4th part is going to be about Wings. And the 5th part is going to be about UBEX. So Wings is the 1 gigabit Ethernet solution from Lightware, and UBEX is the 10 gigabit Ethernet solution. So in total, we are going to have 5 parts, 1 part every week. And hopefully, we will not overload your brain with a lot of information with these 1-hour sections. While we wait for some attendees to join, let's cover some housekeeping items. First of all, depending on what type of device you're using, you will see Gábor's webcam and his shared screen next to each other or on top of each other, or you can actually distribute. If you're using 2 monitors, then you can select GoToWebinar to show the webcam on one screen and the shared screen on the other screen. And if you're watching on a smaller screen, like a smartphone, then you can swipe left and right to switch between the webcam and the shared screen. Since this is a webinar, all the attendees are muted by default. So you cannot speak or turn your webcams on, but we encourage you to send your questions or comments or feedback using the questions panel. Obviously, if you have questions about the topics that Gábor is going to mention, then feel free to type in your question. We are going to have a live Q&A at the end. So if we have interesting questions, then I will ask those questions at the end out loud, and Gábor is going to answer them so that everybody can hear the answer. But if you have any comments that you like about this webinar or certain topics or the way we explain things or some criticism, then please also send it using the questions panel. And lastly, I would like to assure everybody that this webinar is being recorded, and 2 or 3 hours after the session ends, GoToWebinar system will send you an automatic follow-up email, and that email is going to contain a link to the video recording, so you can just open up that link and watch the recording again in case you missed something or you want to go through the material again. So with all the technical stuff out of the way, let me pass the word over to Gábor, and he's going to guide us in the world of IP as far as Pro AV is concerned. Gábor, the stage is yours.
Thank you, Tibor. So hello, everybody. So as Tibor mentioned, we're going to have 5 sessions in this training. And we're going to talk about today is really the fundamentals of IP networking. I'm going to talk about IP addresses, subnet masks, port numbers, and we're going to look into the differences in network communication when it goes in private and public network. Now, in the next 2 sessions, as Tibor mentioned, are going to be also basics. We're going to talk about how IP addresses are generated, what's a VLAN, what's multicasting, what's link aggregation, things that you will see in AV over IP products in computer networking. In session 3, we're going to go and look into networking devices, understand the network switches, the routers, what's a gateway, what's firewall, and so on. In session 4 and 5, we're going to actually look into the individual AV over IP products from Lightware, and we're going to see how to configure them, how to set up the network, and what happens to the products on each and every individual functionality. Now, before actually we go and start the training, let's start with a riddle. And let's see, there's some interesting visuals going on here. Tell me, what do you think? How do you call a place where there's some oil at the root of some tree and under a star named G, and you can have a date here? Well, if you know the answer and understand the riddle, then you already know a lot more than what you will actually learn here. The answer for the riddle is actually multicast network domain. Now, of course, there are many IT tutorials and videos on the internet. Now, however, many of those, we actually looked at a lot of them. Many of them are geared towards IT guys, to IT professionals or future IT professionals. Now, some of you would like to understand this riddle, then you can actually look at some of the videos that will explain the details, but they take about a half hour, 40 minutes, just to explain those individual parts. Now, what we decided is not to send you there and try and find your own answers, because you run the risk that you may actually get more confused and befuddled than when you started looking for answers. Instead of that, what we do is we build our own training materials that is geared towards AV industry professionals. Now, there's a good thing for us because of the high bandwidth that our products use. Us, the AV professionals, we actually surf the waves of network complexity. Now, IT companies have to deal with about 99% of the things that they have to use and do to keep their equipment running. And actually, we're going to be surfing and staying above the waves of these complexities, because we don't actually really need to learn all those details to understand what's actually relevant for our business. Now, if you look at that image there, you can see something like a distribution tree under the waves, something with an acronym OIL, and there's like a star G join and some rendezvous points. So you kind of have a hint where the riddle actually comes from. Now, why is this whole training session important? Well, we are actually entering the world where there's actually the IT world, where the AV over IP products are getting connected, and we're merging our world with an area where the IT guys and the IT administrators are managing everything. So when AV professionals meet the IT professionals, there need to be some sort of a technology overlap, and that mostly will depend on us, the AV industry, because IT professionals may not have seen AV over IP products or AV products in general. So actually, the IT administrators' world is sort of complex. They have their own language, their own jargon, their own acronyms. So there's two things we need to do. First, we need to speak their language, and we need to adhere to the rules that they set in the network. And the other thing is because they need to understand exactly what AV over IP products do on their network infrastructure, we have to communicate and help them understand the procedures that we use. Now, there's a good example already how the IT world influences the AV world. Now, we have a brand new feature set called the Advanced Control Pack v3, and inside there is a new feature called HTTP Salvo. And this is there because the Cisco RoomKit Mini product only communicates our system commands with HTTP protocol on port 80. Now, in other words, it uses probably one of the most commonly used protocols and port number in the world, other than HTTPS. So this protocol is very well known by the IT guys. They're all sort of security answers to the issues, and there's no need for additional security testing if there's a new product that communicates in this protocol. So it's quite convenient for the IT administrators, so they require these standard known protocols to be used in new devices that are going onto their networks. So let me show you a bit of a sneak preview of what's going to happen in part 4 and 5, because we'd like to make it easier for you to learn and actually digest how the communication is going with our products. So what we're going to do in those part 4 and 5 is we're going to actually configure network parameters live. We're going to see the effects of the changes in real time, and we're going to use graphical representations and look at the products and the networks, which is user interface, so we actually visualize what we really do and how the product's changing with those network settings. Now, of course, this subject can be quite deep, as I mentioned, so this is not an IT training. We all heard about some protocols in the past, something like HTTP and FTP, or if you set up a computer, you know what an SMTP is, or TCP/UDP. But let's see how many protocols are there. Well, there's a software called Wireshark. It's a standard network analyzer. So let's see how many protocols that particular software can recognize. It's quite a big list. It's going down, yeah. Well, yeah, almost 2,600 protocols. So Yes, this subject can be long and deep if we want to understand a lot of that. Well, what we're going to deal with is actually the fundamentals of networking. And what we're going to do is we're going to use human communication analogies and human world examples to draw parallels with the computer networks. So let's go and let's see how this works out. Imagine a world where there's when people communicate, when you actually can communicate and talk to someone only if you hold hands with someone. You have to look at that person's face, so you can look at each other's face. You have to somehow remember each other, and you have to call out each other's name in every single sentence. Now imagine that in this world, you can only talk to that person, and you have to speak the same language, and you actually have to clarify this language in every sentence. Now imagine this person that you hold hands with doesn't actually even have a face and doesn't have a name, because that person is just a messenger. Now, if you hold hands with this messenger, then you have to tell that person to who do you want to send your message, who you want to talk to, and how does that person actually look like. And of course, the messenger must hold hands with the other person as well. Now, if you want to talk to someone outside of the room or the area where you are, you need to first find someone who can actually talk to the outside world, who stands at the door, and you have to tell that person that you have a message for the outside world. Now, of course, you need to ask first, well, who's standing at the door and who can talk to the world outside the room? Now, so if I use this basic analogy, here's how the basic communication network flow goes. You have to hold hands with someone first. You have to figure out who's the person you want to talk to. Let's say you ask, hey, who's John? And then you have to wait for John to show his face to you. And somehow you have to remember how John looks like. Now, you get to talk to John by telling the person you hold hands with that, hey, I'm the guy, I'm Jim with the short hair, goatee, and I have a message for John. And the guy, glasses and mustache, and I'm talking in English language and I'm saying hi. Imagine in this world you have to do this every single time, well, except for the hi part, of course. The content would be different. Now, okay, let's name these things, these individual parties. Everybody has hands, which means there is some sort of a communication interface, a physical interface somehow in networking. That could be Ethernet or Wi-Fi, the most common ones. There's quite a lot of them. Now, the people who have names and faces, they are network devices such as computers. We call them network nodes. They can be, for example, the Lightware devices are such network nodes. Now, the messengers without faces and names are actually network distributors. They're like hubs, switches, and extenders. Now, hubs were in the past, that's history. But those actually who stand at the door, and we call them gateways, and they are actually typically router devices. This is something that almost all of you probably already know. Now, routers are like two computers in one. They have two pairs of hands, they have two faces, and two names. Okay, so let's see what they actually do in the network environment. So when computers hold hands with someone, then, for example, on the Ethernet cable they're connected, the LEDs light up. So somehow there's an indication of a physical connection. Now, when the computer identifies itself by its showing its face, this actually means that it's sending its MAC address, which is called media access control address, and it's sort of a serial number. In most of the devices, it's burnt in, it's hard-coded, but in several devices, it's actually configurable. Now, when the computer calls someone by name, it actually means that it uses the IP address, which is the Internet Protocol, and you can see the example number on the side. Now, since we are learning IPv4, as most products still use on IPv4 networks, we actually have four numbers ranging from 0 to 255 that describe this number to create the IP address and IP address related numbers. Now, so when we're sending a message over the network, so what we really have to do is we have to connect first, then find out who's who around us and who is where around us. And actually, we have to tell the device we are connected to physically first who we are. So we have to tell them our own IP address and tell them our MAC address. And then we have to tell who we want to talk to. That would be the destination IP address and the destination MAC address, so name and face. And then we have to identify the protocol we use, for example, TCP, which is a language. Remember, languages are communication systems. They don't define the word and the content, they define the system. And then, of course, we have to send all the data we want. Well, whatever fits inside one packet. And these details are included in almost every data packet in the IP-based network. And we're not going to go into those protocols that don't have these details, but we're going to mention them at some point in the second and the third part of this training series. Now, since you've already heard about layers in some training or somewhere or some documentation, people talked about layer 3 switches and so on. Let's see a little bit what those things are. On computer networking, the steps I defined and described, they're done by the help of different protocols. And those protocols are actually done on different layers. Now on the visual on the side, you can see 7 layers, 4 of them blue, 3 of them red. Now the blue ones are the ones that we really care about with networks. That's what network cards and interfaces deal with. The other 3 is not the network card's job. It's the computer behind it. Okay, so let's see. Well, if I say holding each other's hand, that's actually what layer 1 does. That's why we call it the physical layer. When we're looking at each other's face, that's what actually layer 2 does. That's called the data link layer, the physical MAC addresses. When we're calling each other by name, that's actually what layer 3 does. That's called the network layer, so that's the IP addresses. And when we identify the language we use, like TCP or UDP, or English, let's say, is that what's actually layer 4 is doing. That's called the transport layer. That's responsible for transporting the message. Now, these layers are specified something in the OSI model, and it's actually something that you may have seen before. We're not going to go into the details. I think it's enough for us in the beginning to understand that these layers have these basic functionalities. Now, so far, this is easy, of course, but let's complicate things. Let's see how much we can understand. So when you're trying to set up network parameters in your computer, you get actually help with from your computer, because if you make a mistake, there's some error messages that gonna come up on your computer. Something's illogical or something is forbidden, the computer is gonna tell you. So if you have some of these error messages that I'm showing on the screen, those are easy to decode. Like, yeah, 200 is not between 0 and 255. Okay, and the other one says that, okay, we have some gateway not on the same network, same subnet. So, okay, 2 devices are not on the same network. Easy to understand, fine. However, once we see error messages like this, then we have an issue, because we need to understand what these messages kind of mean. Where is the error that we made and how to fix it? So when you have a message that says that something has to be contiguous and some bits in the host address portion has to be or was set something, yeah, that is a little bit more complicated than just 260 is not in 0 to 55 range. Okay, so well, let's ask a few questions and let's see based on those questions if we can answer all that. So what does the computer do when it has to send a message, let's say inside or outside a network? How does it determine who to send a message to? And whose IP address and MAC address will it use to send that actual message? Well, there's a function in networking called subnet mask. It's actually a numeric rule to help us out. So in order to identify whether an IP address belongs to a computer that's inside or outside a network where I am, here's what I have to do. I have to compare my own IP address to that IP address. And I have to use the rules set by the subnet mask to do this comparison and come to the determination whether or not this computer is inside or outside. Okay, so well, what do masks do? Well, masks, they cover an area that doesn't actually matter. When they actually leave areas unmasked, which do matter, like our noses, ears, and eyes, so we can communicate. Now, this is actually when the terminology and the expression comes from, but it's kind of backwards, because in networking with the subnet masks, it's really what's important is what's under the mask, what's actually being covered. Now, we're going to use a basic example throughout this training, and I actually set up my laptop with these IP addresses, so I wanted to find out if the laptop with the 192.168.107 addresses on the same network with the RAPB511 product, which is 192.168.200. And the rule that helps me out to do that is the subnet mask, which is 255.255.255.0. Now, this number is probably familiar for most of you because you've seen these kind of settings before, especially if you bought a router or a gateway before. Okay, well, first we have to consider something, which is the binary number system. And there's a hint for those of you who did not work with the binary system, or maybe last time you heard it in school. There's a function in Excel called decimal to binary. So it's DEC to bin, and within the parentheses, if you put a decimal number, the result is going to be the binary representation of the decimal number. So it's kind of quite a nice thing to help us calculate the numbers. But let's do this, and let's take my IP address in my laptop. And you see now the binary representation of that number. You see the dots representing the spaces, let's say, between the numbers. So, and here's the representation of the RAPB 511. Now, when I look at the subnet mask that looks like this, then suddenly things starting to look interesting. Something makes sense now. So what happens is somewhere in this area, when there's all of those bits are ones in the subnet mask, the numbers seem to be identical bit by bit. And it's interesting that those two addresses are different in the area when there's all zeros in that subnet mask. So technically, this is what happens if these IP addresses are the same at the part where the subnet mask bits are all ones, and they're only different where the bits are zeros, they are actually in the same network. So what we're saying is where there are ones, they are masked, and when there are zeros, they are unmasked. Simple as that. Now, there are actually special rules in the computer network, and the number one is that there cannot be a computer in the network with an address that has all the zeros or all ones in that area, which is unmasked. So meaning when there's all zeros in that subnet mask. So the green zero representation, that's the area or block, right? And I'm calling it block. And if in that block or area, all the bits are zeros, like a 192.168.1.0, that's not a valid IP address for a computer. If it's all ones in the same area, that's also not a valid IP address for a computer. That's the rule. And now, if you look at that error message, it says bits in the host address portion all set to ones and all set to zeros. This is actually what they mean. So if you set up an IP address that looks familiar and looks okay, because of the subnet mask, it may say, hey, that's not valid. It's not a real computer. You're not allowed to use that. Now, in this well-known 255.255.255.0 mask network, I can actually have 256 numbers. The last number can be from 0 to 255. However, value 0 is all zeros at the end, and value 255 is all ones in the end. So those cannot be IP addresses of devices. They have actually special meanings. Now, the other 254 addresses, they can be computers. Now, of course, subnet masks often have different than 0 and 255 values. In fact, it's quite a rare thing to see in real network environments all 255 and all 0 subnet masks. You can have them in your home router, and that's fine, but in large networks, not that often that you can see these ones. So we need to look into other numbers. Now, the rule here is the subnet mask left side must be all ones, and the right side must be all zeros. And where the left and right side ends, or where they meet, is up for us to determine. Now, there cannot be mix of ones and zeros, so I cannot put a 1 between the zeros, and I cannot put a 0 between the ones somewhere, which is actually both helpful for us, and it's also a little bit complicated. Let's see why. So the less zeros we have on the right side, the less devices can be in the same network. So when you see there are 8 zeros on the top with the number ending 0, so there's 8 bits, and that's 256 numbers in it. But once the numbers start going up from 0, like 128 and 192, then you can see that those ones are appearing at the last block, and you get less and less zeros. That means that you can have less and less computers inside a network that is defined by that subnet. Now, adding together numbers from left to right, like 128 plus 64 plus 32, is something that makes the calculation a little bit complex in the beginning, especially if you're not used to binary numbers. However, in the error message, when I said something has to be contiguous, this is what it actually means. It has to be a continuous flow of ones, and somewhere it has to switch to a continuous flow of zeros. No mixture, and that's what it means that it has to be contiguous. Now, if we're looking at the subnet, and this is the subnet rule that defines the size of this network, then let's see, there are some IP addresses. And let's look at those. If there's all zeros, this is something I call the network address. It identifies the network itself. Now, I don't want to overload you with a lot of technical terms. So what we're going to do is at the end of the training, or after the question portion, we're going to run a few slides automatically. And in those slides, we have the official terminology of the terms. So those are the appendix slides. So we will tell you exactly how it's called in the network world. Now, let's go back to the other numbers that are 1s to 254. So there's a mixture of zeros and ones in that last block. And these are actually, let's say, the first and last computers on this network. And of course, all the numbers in between are the rest of the devices. On the bottom, you can see there's all ones. And I mentioned this is also something special. This is called the broadcast address. And whatever is sent here, any computer sends something here, that's actually going to be sent to everybody. Well, that's what broadcasting actually means. Now, without all bits and these numbers, let's visualize it and let's see how it literally looks like. So, as I mentioned, 0 and 255 are forbidden. And there's an interesting, not a rule, it's more like a typical application use case when the gateway is quite often the number 1 on the network. So it's a real device, and also from 2 to 254 are real computers. So it seems quite easy and quite logical. But you know what, let's go back to the complex stuff and let's continue with those numbers. Okay, so here's my network. I mentioned something, 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 0 to 255. Now, I simplified it so it fits on the screen. What happens is suddenly, somehow my network splits into 4 pieces. Now, because of the subnet rule is actually what happens, so that my 254 real computers are no longer in one network. But, you know, things are missing from the screen. And let's see why how and why did this happen actually. So what happened is I used the subnet mask ending with 192. So I only have 64 numbers in one network, and my numbers from let's see, 0 to 255. So all these 256 numbers belong to different networks now, because the subnet mask ending with 192 means only the last 6 bits can be different. Now you can see there's quite a number of red zeros and ones in here. So because these 4 addresses now, because they're all zeros in the area where the subnet mask is 0, the green area, these 4 addresses cannot be used anymore. Then of course there's all 4 of these networks have an address 1 or a computer 1. And there's of course a last address on that subnet or a small network. And of course we have 4 computers with all 6 bits are ones, or so IP addresses with all 6 ones, sorry, and they cannot be used either. So, okay, there's something interesting going on. Now, what happens is this subnet mask allows only 6 bits to change. So we have 4 networks or subnets. And instead of only losing address 0 and 255, I'm also losing 63 and 64, 127, 128, 191, 192 because of the subnetting thing. Now, when I look at those little bits in there, I can actually identify these subnets and say, hey, they actually indicate the binary representation of the 0, 1, 2, and 3. And that's how I can call them like subnet 0, subnet 1, 2, and 3. So, okay, it's fine. But let's see an example. I'm not going to give you the hint how many other errors are on the screen intentionally, but we're going to look at that particular host bit 0 thing. So 200, I said it's a valid address. Well, actually what happens is because the 252 is the last number in the subnet mask, it defines that we'll only look at the last 2 bits and we can only allow those 2 bits to be different. And because those 2 are zeros, they cannot be real computers because those 2 bits are zeros. And the 107, which I also used before, suddenly they are also a problem because of the same error. And the same situation goes here because the same address 107 was valid before, but the subnet mask 252, looking at the 2 bits, 107 has 2 ones in the end, so that also cannot be a real computer. So all I had to change is the subnet mask and suddenly an IP address is no longer a valid computer. Now let's look at the real small system example. Use the same example I mentioned before with the Lightware product in there. So what we have here is my laptop with the 192.168.1.107, and the subnet mask is the classic 255.255.255.0. And the RAPB511 has its IP address almost as mine, but it's ending with a 200. So what's going to happen is the computer is sending a message, and it's going to look at the source and the destination IP addresses. And it's going to look at the mask and say, well, the mask allows all the 8 bits to be different in the last 8 bits, let's say the last number. And okay, they are different, but the rest of them are identical, so fine, it's on my network. We're in the same place, so let's fire the package to the RAPB511 directly. However, if I change that subnet mask to 192 at the end, then the story is different, because now the laptop's going to look at the source and destination IP address, and now there is a difference in 2 bits, the first 2 bits of that block, where there's ones, those should not be different. And if they are different, that means they're not in the same network. So the laptop simply changes the MAC address to the router's MAC address. And what it's going to do is going to send it to the router and say, please forward it to the IP address, the destination, because it's not in my network and I cannot talk to it directly. Okay, now I'd like you to try something. I'd like to ask you to try something when you have some time. Now, if you go to your computer's command prompt or PowerShell in the newer Windows and type in a command called ARP --A, the computers will actually going to show you how it remembers John's name and face from the original communication example. This is what they call an ARP table, or address resolution protocol table. This is actually what links the IP addresses and the MAC addresses together. So on the screen, you see internet address, the IP address, and physical address, that's the MAC address. And all the IP address in there that this computer knows, and it allocates all the MAC addresses that linked to that particular IP address. So this is how it remembers all the time who's who. Now, I'd like to give you a little bit of jargon hint, because when you talk to the IT guys, they use a lot of special terms. Now, in an IPv4 network, the IP addresses have these 4 numbers, and they are called 4 octets because they have 8 bits. And so actually an IP address is 32 bits. Now, officially, there is a way to describe IP addresses and subnet mask in one form. So we represent it in one way, and that's how it looks like. Let's say 192.168 something something /16 or per 16. And this, what it means is the first 2 block numbers, the first 2 octets can be, and actually have to be, identical, and only the last 2 numbers can be different. And this is when the subnet mask says 255.255.0.0. So that's what it means now to understand. Now, if they say something like 192.156.0.0/24, what it means is that the first 3 numbers have to be identical, and only the 4th number can be different. And there's our classic 255.255.255.0 subnet. So this something something number actually represents the number of ones in the subnet. So a per 24 or /24 subnet means there are all those ones and the zeros. That's actually 24 ones. So in the jargon, the IT guys will actually simply say per 24 or /24 subnet. In this case, they will typically not mention the IP address. They know it doesn't really matter because it's the subnet mask that determines who's where and who's who on the network. Now, okay, this is fine, and that's how IP addresses work, but let's see how they actually work when we go into private and public networks, like home network and the internet. There's some interesting thing going on. And in order to explain this, I'm using an analogy of trains, because many of us know how trains and public transportation work. So imagine a train which changes its from label every time it leaves a major train station, but before it reaches a destination. So, and imagine if it changes its to label as well somewhere at the end of the line. Well, how would people know at the destination terminal, train terminal, where this came from and which platform we should send this train? Well, we cannot ask the passengers, of course, so we cannot look into network packets for that. So if we take an example of a train from Munich, Germany coming to Budapest, Hungary, and it travels to Salzburg, Linz, and Vienna cities in Austria. In this particular example, we would consider Germany being a private network, Austria would be an internet, and Hungary would be another private network. So we actually have a problem. Well, There's no Vienna in Germany. There's no Munich or Budapest in Austria, and there's no Salzburg in Hungary. So these are actually invalid depending on where the train is at the moment. Now, for us in the human world, this is not really a problem, but in computer networking, these are real issues. So we look at the train as humans and say, oh, it's coming from Munich to Germany, fine, doesn't matter where I am, it's going from Germany to Hungary. But in the networking, we actually need some more help, and we need some intelligence, if you will, to let the train out of a country, get it across the other country or internet, if you will, and allow it to get inside the third one somehow. So in the network environment, this train ride would look something like this. If the train's inside Germany, it would say, I'm coming from Munich and arriving from the main terminal. And I'm going to the Austria-Hungary border, and I'm going through Germany-Austria border. Now, once I'm inside Austria with this train, it says now it's coming from the Germany-Austria border and arriving to the border station. It's not from Munich anymore because there's no Munich in Austria. Now, going to Austria-Hungary border is the target destination, and we're going through the Linz train station. Now, those are valid in Austria. Now, until this, it's actually easy because getting all the way to the destination area's border, let's say, or let's say the edge of that area, it's almost automatic. This is actually what networks mostly do if you go to the internet with your computer. Now, the trick comes when we go inside Hungary. Well, first of all, we need some special rule or policy that we need to actually let the computer in the country. And then suddenly it's coming from still Germany-Austria border, and it's arriving through to the Austria-Hungary border, but now it's going to Budapest and then to the West train terminal. So the two address changed somehow. Now, this entire process that I described with this analogy with the train is called network address translation, or NAT in acronym. So in other words, actually, there are major differences in private and public networks. So one of it, for example, is that we cannot directly address a computer from one private network and going inside another private network when going through the internet or the public network. So if I have two computers, they have very similar IP addresses, 107 ending and 11 ending, but everything else is the same. Okay, well, what happens is I have to get out of my small network and I have to go to the router or gateway. That's the one that's connected to the internet or a wide area network. And that wide area network goes all the way to the edge of the other network. But then we actually cannot go inside. So here, what we need is we have to send our message to that last visible public destination address, which is the router between the green and the red dots. And somebody there has to help us to deliver that message inside the private network. Well, that's actually going to be the router, or it's called the firewall, that will let us do that. And this is the first rule. The other rule is private IP addresses are in private networks and public IP addresses are in the internet. But actually, private addresses cannot be used on the internet. Internet addresses or public addresses are visible in private, of course. That's how we get out to the internet, but private addresses are not visible on the outside. So the most commonly used IP address in the world probably is the 192.168.0.1. If you buy a router or a gateway or a firewall device or something in the local computer store, this is probably what it's going to come with. So if there are millions of these IP addresses in the world, we have to get to those devices. Somebody has to help us. So what actually happens is, let's say if I have two computers in the same network, 107 and 108, 107 wants to go out to the network. And what it does, it's going to send its packet to the gateway, and the gateway is going to actually change the from IP address. So this is where the from Munich to is changing, and instead of 192.168 something something, it's going to be like some 89.132 or something. That's actually a valid IP address on the internet. And if the 108 wants to go out directly and try and connect, it's not going to work because that's a private IP address. It's not valid on the internet. Now, that's fine, okay, this is logical, but what about this train station platform number and tracks and stuff? How does that work? Well, since both Munich and Budapest train stations have multiple tracks and platforms, the system actually maintains an additional pair of numbers. Those numbers identify where the train came from and where it's actually going. Now, this is set up so the train goes to the correct track and the correct platform. Now, these numbers are stored and actually maintained, well, really changed back and forth all the time in every station along this entire trip. And this number is especially important in the border station, let's say, of the edge of a network when we're letting the train or the packet in the destination. And this means that when a train goes back from Budapest to Munich, everybody knows where and how to send it back. And this is done by these numbers called source and destination port numbers. Okay, so let's see how this actually works. So this train network actually knows in Munich with these numbers that from which station and which platform it has actually came from. When we're in the regional area in Germany with the train, the network knows from which city and which regional track it has come from. Now in Austria, it actually knows which country it came from and through which, let's say, national track it's going through. Now in Hungary, it knows still from which country it's coming from, and it also knows which regional train track it's coming through. And in Budapest, it actually knows to which train station and to which platform it should go. And this is all needed to be used and remembered so the train can actually go back to Munich. Now, okay, let's stay away from this analogy for a little bit and let's see a real life example. There are some computer servers on one side on the internet, let's say the lightware.com domain. There's the internet with 2 routers simplified, and there are 4 computers, let's say, for laptops. One of them have multiple applications open, Outlook, an internet browser, the LDC from Lightware, and some Windows application. And actually, in the internet browser, there are 4 windows. So what we do is we're going to type in the browser name, let's say the domain name, and we're going to send that message out to the Lightware server. And of course, the package is going to come back as an answer to the same window in the same computer, same application, and we get the website. Of course, we all know that this is how network works. We experience it all the time. Okay, so let's go back a little bit to this train analogy and see how this communication actually works. So when we open the internet browser and we call up this website, the lightware.com, the source port identifies the web browser and the session of which window is open. Let's say which internet browser open, we called up the website. And for example, in this case, it's a big number. It was a big number, 63,910. Now the number, this big number actually is constantly changing in a computer. So when we open up a new window or call up a different website, those numbers are going to actually change. But this number would actually mean that, hey, this train is from Munich main terminal and it's coming from platform number 1. And in the destination port is 80, let's say, to tell the destination device that it wants to reach a web server and request an HTTP content. This actually means in the analogy that this is going to the Austria-Hungary border station and he wants to go to track number 2 towards Budapest. Okay, so when we use this network communication example, when we have the response coming back from the web server, then it says the source port now is 80, and it is indicating that this is the web server's answer to the HTTP message request. It will actually be addressed to the destination port 63,910, the big number, and we're going to identify that with this is actually the internet browser specific window and page from where we actually requested this website. Now, of course, there are many of these processes go on simultaneously in a computer. So, you know, we have to make sure that we get the emails in Outlook, the PowerPoint file opens in PowerPoint, and now we get the website content, let's say internet browser, Google Chrome. Now, any of these numbers get confused, deleted, corrupted, whatever, the message will be lost and we have to resend the request. Well, something we're already familiar with, doing that all the time. Now, let me give you a real example. This table has quite a lot of numbers. What it is actually is a Vinx data communication. I used jumbo frames of a 1080p video stream for 33 seconds, and I looked at all the traffic. And what we're really interested in is this block, because those are the source and destination port numbers to do various communications between devices. And each and every one of those number pairs represent a different method, a different content, and different communication. One of them actually has quite a lot of data because that's the video stream, but the rest of them are specific communication packets. So this is actually how those port numbers are being used, not just in a computer with like Outlook and PowerPoint, but also in a device like Vinx. Now, there's a fun thing for you to try. Now, we already looked at the command prompt, so there's a simple command actually where we can find out how a computer reaches devices on the internet. So what I use the example Lightware.com and Microsoft.com. And this is called the trace route. And it's typed in trace RT and then space, and you put in the domain name of the web server like www.lightware.com. What you're going to see is the number of steps, how the package travels from your computer to the destination. So you can see a cable TV provider and then something with Hungary Budapest and another Hungarian cable TV or some sort of internet provider. And finally, in 9 steps, you get to the Lightware.com website. Now, in Microsoft case, my computer goes out to the cable TV provider. It goes to some HUMON city, actually, and then goes to Budapest, and then ATV, that's Austria, Vienna. So, and then goes to some strange number, and finally it reaches the destination IP address. Now, on this screen with this thing, you can actually say, hey, there's quite a lot of timing going on and a lot of IP addresses on the same screen. But this is how you can actually understand how a network packet travels and changes those, let's say, even the IP addresses. How many IP addresses need to be known by the system? And now with this, we actually reach the end of the first part. And let's see if we have some questions. Before we go to the questions, however, I'd like to mention that, as I mentioned, didn't want to overload you with all the technical terms. So once we're done with the question part, Tibor and I will actually sign off and say goodbye. But after that, the presentation is going to actually continue for a few minutes. And in those few minutes, we're going to show you 7 appendix slides, and we give you the exact technical terms of the things that I called groups and blocks and stuff like that. And I'm going to give you actually very useful information, typical IP addresses, subnet masks, and some other useful things for the basics. So you don't actually have to watch the whole thing and stay here for an extra 7 minutes or 3-4 minutes, depending on how long we run that. But when you have the recording, the link, then you can actually look it up, and you can just click on the area and see the technical terminologies that we should be using if it's a, let's say, IT training. With that, I'd like to give the control back to Tibor.
Well, thank you, Gabor. That was an excellent presentation. So please, if you have any questions, now is the time to type them in, and Gabor will be able to answer them here live. If you think of any questions later after this session ends, then please feel free to send us that question to training@lightware.com or support@lightware.com, or reach out to your local representative, and maybe they can also answer. So, first question: what's Lightware's recommendation on putting AV devices on the same switch as the Office devices connected to the internet?
Well, if you have to do that, then I would recommend to use VLAN functionality, which we're going to talk about the next training. And you need to separate the communication completely from the other devices, because you don't know what those computers are going to communicate, how much data they use, and how much broadcast and multicast messages are going to go across. So if you have to do it, make sure that you isolate your devices, and that's one of the functionalities. It's called the VLAN.
Yeah, that's another question. So what's the difference between subnets and VLANs?
Well, actually, the difference is subnet is a numeric rule, and you can actually go from one subnet to another. So there's a device, that the gateway that can actually help you. However, a VLAN is a kind of a label system that is intended to completely isolate networks from each other. So there should be no cross communication between these VLANs or logical grouped computers. They should not see anything from each other, and they should not bother each other with the communication.
Yeah, so subnets actually is a way for devices to think they are in one network or another, and that's why you can mess up the settings.
Correct.
And believe it or not, I think that the most common problem our customers report to us when they are setting up systems are related to subnets. They are either too big or too small, or the devices are in different subnets. So that's why we started with explaining, and that's why we went so deep into explaining subnets. We know it's not an easy thing to understand, and we don't expect anyone to decode subnets after this webinar ends. Very few people can do that. Actually, IT administrators can do that. I myself also need to look it up and calculate subnets.
Yeah, actually, when there's a network problem, that's the first thing you need to look at, the very first thing.
Yeah. True for computers, laptops, and also true for Pro AV devices or AV over IP devices. Okay, a video for meeting needs to arrive close to real time. It doesn't need to be in packets. These protocols seem overly complex for video.
I'm sorry, can you please repeat that?
I think this person was referring to video conferencing solutions, so not Pro AV solutions. But actually, can you let us know about the latency of Wings and UBEX, Gabor, since we're talking about close to real-time video?
What do you mean the latency, how the device's latency requirements?
Yeah, well how much latency they introduced to the signal?
Well, actually, there's no actual frame delay, added frame delay in those products because of the technology they use. So we actually do real-time communication. The latency is added by network devices if they have to travel through multiple devices and multiple long communication cables, let's say. So what we need to know is what latency the network adds so to impact our products, especially when we have like IP audio like Dante going parallel with the video over IP.
I think Wings adds 1.1 frame, and UBEX, you can set it up UBEX to have just few lines of latency, or if you need seamless switching, then it's one between 2 frames of latency. So UBEX has 2 modes of operation. Okay, I'm just scrolling through some thank you messages. Thank you, thanks guys. Will you cover differences between managed and unmanaged network switches? Where is it recommended and where not?
Yes, in part 3, we're going to talk about network switches, and that includes like layer 2 and layer 3, and also managed and unmanaged switches. And the recommendation, especially look at how many applications, if there are, for unmanaged switches to be used.
Okay. Well, we got a question regarding RU points or AVIXA RU points, whether these trainings are certified or not. Not yet. When we finish the material, we are going to apply for a certification, and I think the 5 parts in total will be 4 points. When we have that certification, then we will let you know. You will have to fill out a quiz, and if you pass that quiz successfully, then of course we can send you the certificates to claim your RU points. Okay. For what purposes we need public IP from our internet service provider?
Well, the IP address, the public IP address is needed so we can actually talk to the internet, because the IP address we have locally cannot be used outside. So when we have, let's say, an internet gateway, the gateway device needs an IP address, and that's actually the face and name of the public side of a router. So that can communicate, and when it communicates to the internet, it uses its own IP address to say where it's actually coming from. So that's going to be our from IP address when it goes out to the internet.
Okay. When will part 2 to 5 happen? Will we get another email invite? Yes, I think just 40 minutes ago, the invitation for the second part, which will be held next Tuesday. So Thursday is a holiday in the US, so we moved both sessions, both our morning and evening sessions, to Tuesday. So please take a look at your inbox because you probably got the invite for the second part. Or go to our website, and we have a training calendar. You can also find these trainings on our website, and you can register if you're still interested in hearing more details. Okay. Just a few thank you messages. All right, I don't see any more questions, and the hour is almost up. So I think it's time to wrap it up. Thank you very much for everybody who could join us today here and live. I hope you found the information that Gabor has shown you interesting and useful. But of course, please come back for the second and the third and fourth and fifth parts because we will cover much more using the same explanations. So hopefully we could make it interesting enough for you. We watched a lot of IP trainings ourselves, and we wanted to do something different. We wanted to be less technical, but of course being authentic and not making any mistakes. So hopefully we gave you, or Gabor gave you, examples which are easy to understand, and you can use that knowledge in your day-to-day work. If you would like to test out our 1 gigabit solution Wings or 10 gigabit Ethernet solution UBEX, we can certainly send you a demo unit. So please reach out to your local Lightware representative. If you want to play around with our devices, see what they can do, then we can, of course, make that happen. If you have any questions about these products or IP solutions, then please go to our website, www.lightware.com. And if you don't find the answers you're looking for there, please also feel free to reach out to your local representative, and we will find the best person to answer those questions. Again, this webinar is being recorded, and I think in 2 hours after this session ends, you will get an automatic follow-up email from GoToWebinar, and that email is going to contain the link to this recording. And one final thing, when this webinar ends, you will be prompted to fill out a short survey. I think it has 5 questions. We would really like to know your feedback about this webinar, what you liked, what you disliked. Please give us your feedback if you have 2 more minutes, because we always try to improve how we deliver these trainings, how we put together the material, how we present it, what is missing, what we explained in too much detail, which was boring for you. So any feedback you have, we would really appreciate it. So Gabor, thank you very much for doing this training, and thank you for the attendees for joining us, and hopefully we will see you in the second part next Tuesday.
Yeah, thank you. And I'm going to start then the next 7 slides. This is where we sign off, and the next few minutes you're going to see the technical terms in appendixes.
Yes. Okay, go ahead.